expect on your class test next week. That's all there is as far as an intro is concerned. So Josh, would you like to do the first question?
Right. So this first question was taken from version 7A, session 2, 2009. It's a fairly short question, but to solve it, you really need to remember your, well, you really need to remember some things about sec and tan and all those functions. So a nice thing you can do here is to remember that sec squared is actually the same as tan squared plus 1. So I can write that this integral is the same as the integral of tan squared x plus 1 sec squared x dx. And the lovely thing about this is I know that the derivative of tan x is sec squared x. So I can, well, I could do a substitution, but actually this is one of the cases where I think I could probably just integrate it straight away, just pretty much by looking at it. So if I want to integrate, well, let me expand it maybe just one step. So it's the integral of tan squared x sec squared x plus sec squared x dx. Well, this second term is quite easy. The integral of sec squared x is just tan, and because I have this sec squared here, this is just going to be essentially tan cubed, but not quite. So if we do this correctly, it's 1/3 tan squared, 1/3 tan cubed x plus tan x plus a constant, and that's my answer. And maybe let's just quickly verify this does actually do what I want, that the derivative of this is this. So this first term, take its derivative, I get a 3 tan squared, so I get 3 over 3, 1, tan squared x times the derivative of tan x, which is sec squared. So I get a tan squared sec squared. And derivative of this is sec squared, and I have my arbitrary constant. Okay. So it's a fairly quick question to answer if you know how to do it.
Alright, and I just pumped up the volume a little bit as well. Did I want to say anything about this? The only thing I'd add is a kind of just a thing to speed up your class test is to call something like this I, like that. And then instead of writing all this stuff, you can just write I equals, because you might have to write this integral several times. So it's just a more convenient way of writing this integral. You just call it I. It saves time. No, looks good. Looks good. Plus C, always important for indefinite integrals.
I think one thing I would like to say is I tend to forget exactly what the relationship is between tan squared and sec squared. I just remember there is one. All this really comes from cos squared plus sine squared is 1. So you should be able to rederive this relationship in a pinch if you need to. So if you're not sure you're getting this relationship right, just quickly jot down somewhere a derivation of it. So expand, you can take tan squared, replace, well, yeah, there are many ways to do it, but just give it a try.
Yeah, I like to do something cheap and nasty, like if I just, on a page, I'd write something like cos squared plus sine squared equals 1, just as a kind of something that I'm about to cross out, because I need to know where the pluses go and the tans, and I divide everything by cos, and I get 1 plus tan squared equals sec squared, and I know that's the relationship. I don't want to, I mean, this is just rough working for me, so I'd hide that from my marker, because they're not going to understand what I'm talking about, but this is just a really fast way of ensuring you have the right thing up here. Alright, next question. here's a question that asks you to use the chain rule to find the derivative dz dt, where the z is given to you as a product of x and y, and the x and y are themselves functions of t. The question explicitly asks you to use the chain rule. So what you are not supposed to do is just put the write z as 8 times cos of 3t sine 3 of t and then use the product rule. No, no, no. You have to, the purpose of the question, as it's stated, is to use the chain rule to do this. So you have to use the chain rule. There's no choice here. So we're just going to write out dz dt, which is equal to d dt of x, y, because that's what x is. Now, no, I'm doing it as the product rule. I'm doing exactly the thing that I said not to do. I'm doing exactly the thing I said not to do. When you look at x, so disregard for a moment what x and y actually are. When you look at z, it's a function of x and y. So to apply the chain rule, you have to take dx dt and then take its derivative with respect to each of its variables. So this is partial z partial x times dx dt. So this is the first variable of z, and then I add dz dy times dy dt. So I look at all the variables that z has. It has 2 variables, and I apply the chain rule, which just tells me that the derivative with respect to t is the derivative, or is the sum of the partial derivative of z with respect to x times dx dt, and I do that for each of its variables. Okay, and notice I'm using the partial derivatives here. This is the partial derivative. This is the derivative proper. I can replace partial derivative with derivative proper here because x is a function of only t. So you could write del x del t here, or you could write dx dt. There's only one variable, so it's the same thing. Great, and now I just fill in the bits. dz dx is just y, treating y as a constant. dx dt gives me, see, cos goes to negative sign, so that's negative 6 sine of 3t. And over here I have the del z del y, so it's the partial derivative of this with respect to y, which leaves me with x, dy dt, and that gives me 12 cos t, cos of 3t. And now I fill in what x and y are in terms of t. That's y is 4 sine t, so that's 4. I keep saying t, I mean 3t, times negative 6 sine of 3t, plus x is 2 cos t, so that's 2 cos again, which I can write as negative 24 4. And this one is 24 cos squared. Good. The most important part of this is to have used the chain rule to get there. Josh, any comments about that?
No, I mean it's a fairly straightforward question. I mean, yeah, it's very tempting to substitute in x and y as functions of t, but that's not going to get you very many marks if you ignore the instructions. So, I mean, the rest looks fine. I think it's important to probably put it back in terms of t once you've done it, get a nice function of t in the end. And you can simplify this slightly, but there's no real point.
Yeah. This is a 2-mark question, so if I was marking this, I'd assign 1 mark to just having that equation, and then another mark for having the right answer. Do you think that seems fair?
That seems like a fair marking scheme.
Yeah.
Accuracy and knowledge.
Yeah. How many marks would you give someone who didn't use the chain rule to do this question? I'm tempted to say 0.
Well, I guess I'm a bit more lenient. Maybe half out of
half. No. You're too lenient. All right. Next question.
Sure. Alright, so the next question I'm going to do is, well, we're given a very particular function here. So z is this particular function cos of x plus 2y. And we just want to show that actually this function satisfies this equation here. So if you take 4 times the second partial derivative with respect to x and subtract off the second partial derivative with respect to y, well, it should calculate out to 0. So they're very nice of you. They're actually giving you a very explicit function here. You can actually do this question where this is an unknown function. But here it's very nice. So let's calculate what the partial derivatives are and verify this relation. Okay. So what is the partial derivative of z with respect to x? We'll need that first. We're going to calculate the second derivatives. So dz dx, well, that's just going to be the partial derivative of cos x plus 2y. And chain rule here tells me that this is just going to be derivative of cos times derivative of the inside. Cos goes to minus sine, so it's minus sine x plus 2y. And I'm going to multiply that by the derivative of the inside with respect to x, and that's just a 1. So I don't really need to write that down. And well, actually, let's just go and calculate straight away what this second partial derivative is. So del squared z del x squared is equal to, well, it's going to be the partial derivative of this term. So it's the partial derivative of the first partial derivative, which is the partial derivative of this, minus sine x plus 2y. And if you calculate that, well, derivative of minus sine is, well, sine goes to cos, so it's minus cos x plus 2y, again times the derivative of the inside with respect to x, which is 1. So that is the second partial derivative with respect to x. So now we can calculate this term, the second partial derivative with respect to y. So let's just do this in one step. So it's going to be the second partial derivative of the first partial derivative with respect to y of cos of x plus 2y. It's a little bit crowded now, so maybe this isn't a good idea, but first partial derivative with respect to y, it's fairly similar to what we had before, except for that 2 there will give us a factor of 2 out the front. So if you take the derivative, you just get minus 2 sine of x plus 2y. I now want to take the partial derivative of this, which, well, another 2 comes out. So again, sine goes to cos, it is minus 4. The cosine of x plus 2y. Okay, so I've run out of space here, so I'll just finish the question down here. So we have second partial derivative with respect to x, second partial derivative with respect to y. Let's verify it satisfies that. So hence, I take 4 times the second partial derivative with respect to x minus the second partial derivative with respect to y. Well, I'll just plug in what I found. It is 4 times minus cos x plus 2y. And I'm subtracting off this term, which is minus 4 cos of x plus 2y. And, well, that's minus 4 times that. These two minus signs become a plus. It is actually just equal to 0. And I will just finish it off by saying as required. So we've shown what we were required to show. So I think that answers the question. Any comments?
No, I think that looks fine. It is similar to something that is one of the questions from chapter 2, but it's a much nicer kind of version of it because you have cos instead of some unknown function. Looks lovely. Well done.
Yeah. Okay.
Let's go next question. Maybe we could talk about how you would mark such a thing. This is a 2-mark question.
I believe it's a 2-mark question. Yeah.
How would you go about this? I'm thinking this is worth a mark, maybe 1 mark here for these two. Just being able to calculate the derivatives without actually putting it into this equation at the end. So I think 1 mark for that, and then another mark for being able to just put all that stuff into the question they were asked.
Yeah. Yeah, it is. Yeah, I guess there has to be 1 mark for the answer, for showing what was required to be shown. So the other mark has to be for calculating these derivatives
accurately. Okay. We did pick hard questions too, by the way, so if you're sitting there thinking, man, that's easy, they're doing the easy ones. Well, we're doing the easy ones first. Okay. Use a trig substitution to find this integral, and I like calling my integrals I. So let's call it I. Well, we need to use a trig substitution. There's a square root happening in here, so hopefully our trig substitution can get rid of that. The first question is, which trig substitution? So I'll start with a few candidates. The first candidate is to use cos t squared plus, and somehow rework this to fit that shape up there. This thing has a constant plus something squared, so I'll have to divide this by cos, and I get 1 plus. Okay, now we're kind of looking more and more like this object on the bottom, except the object has a 4 there, so I might write this as, let's see. So if I take x to be 2 tan t, then this object in here will become just 4 sec squared t, and I can take the square root fairly easily. This informs me about how I should make my substitution. So I'm just starting with this, this identity and reworking it until it looks like the bottom thing here that I want to simplify. So I'll let u be equal to tan, I'll let x be equal to tan of t. Now, generally speaking, I prefer not to use tan and sec substitutions. I prefer to use sine and cos, or hyperbolic sine or cos. So I'm feeling a little bit uncomfortable with this substitution. But the question tells me to use a trig substitution, and that by that they mean sine, cos, or tan, or sec. So I better just roll with it, even though personally I think we should be using a different substitution here. Let x be equal to 2. If I want to make this substitution, I need a few things. I need to rework my dx, and I need to rework my limits. Then dx is equal to 2 sec squared t dt, and when x is equal to 2, then that means that t has to be equal to pi on 4. So when t is equal to pi on 4, this is 1 and that's 2, so x is 2. When x is equal to 0, t is equal to 0. So I can rewrite my integral, which I've conveniently called I, as the integral between 0 and pi on 4 of, well, dx became 2 sec squared t dt. And this thing down here is the square root of 4 plus 4 tan squared t cubed, like that. All right. And I'm apprehensive, but let's see where this goes. So this is 0 to pi on 4, 2 times sec squared of t. This I can simplify to 4 sec squared of t. So that's, maybe I'll write that as 2 times sec of t squared, and then cubed, and then square root of all that. So this is dt. Two times sec squared of t, and this simplifies. Well, the 2 and the square and the square root cancel, and I get left with 2 cubed sec cubed of t. Just, if you like, cancelling that square with that square root. And there should be a dt there. And fortunately, lots of other stuff cancels as well. That 2 will cancel with 2 of those, so I get left with that's a squared. Most of those cancel with most of those, and I get left with an integral I could do. 0 to pi on 4 of 1/4, and this is 1 on sec, which is just cos t dt. And that's 1/4, let's see, the derivative of sine was cos, so that's sine. So that's 1 on 4 root 2. That wasn't so bad. You had to use, I think, a trig substitution to do this. When the question tells you to use a trig substitution, you kind of have to do what they say. But in this case, it worked out all right. Josh, any comments about that?
No, I guess one thing I'd say is they weren't trying to make it hard for you. You can see that in the end, you had an integral that you should be able to do. So that's another peril of ignoring the instruction. If they tell you to do a trig substitution and you don't, I'm not sure what you would get at the end, but it may not be as nice.
It's probably quite ugly if you ignore the instructions, but you can't ignore an instruction like that. Use a trig substitution, you can't ignore that.
Right. And yeah, so always please remember to do the change of limits. You don't want to have to move back to your original variable. It's nice now that everything's in its variable t. So was this a 2 or a 3 mark question?
This was a 2 mark question. The heavy ones are coming at the end. What would you have thought for assigning marks to this question? Of course, one mark has to be for that, just getting the right answer. But where would you have, say, given them 1 mark?
It's hard to say. I mean, knowing what substitution to do is very important, but also someone who didn't do the change of limits, I feel like that has to be. It's not full marks if you don't do that. In fact, you can't finish the question, so you lose that mark at the end anyway.
So maybe to the point of a student who can successfully make the right substitution gets 1 mark, and then another mark for being able to fulfill that, or then being able to do the integral with that substitution.
Yeah, that sounds fair. To me, at least.
Yeah, I think that's all right. Good.
And I really like this technique. Usually I'm working from memory about which substitution looks good, but starting with this fact and getting to your substitution, that's really nice.
Yes, my memory is lacking, so I always have to start with that. There's extra stuff there now, isn't it?
Yes, I think the water. Well,
Alright,
should be fine.
we'll peel it off eventually.
Alright, so I'm going to try and answer this question. It's a little bit wordy, not too wordy though. So we have an equation for a surface here. Here it's given in the form z is equal to some function of x and y. We're given a point on the surface and 2 things we need to do. So the first thing we need to do is find a normal vector n. This is the first thing I'll try and do. And then once I have that normal vector, I can write down the equation of the tangent plane at this point. So the technique I'm going to use here is going to be it's a technique I like because it's a bit more general. It doesn't just apply to functions of this form, it applies to more general implicit equations. So I'll start this way. We can rewrite, I just need to set something up, the equation for the surface as, that could probably compress that sentence, but one way to rewrite it is as the following. A certain function of x, y, z, in this case I'm going to make it x squared y minus 2y squared plus 3x, and bring this term onto this side to get a minus z is equal to 0. So this function equal to 0 defines my surface. Has normal vector. Well, what's really nice, and what's really nice about writing it this way is there's a fairly almost symmetric way to write down what the normal vector would be. You just get the vector whose components are the partial derivatives of this f. And I'm actually looking at a particular point. I'm looking at the point 1, 1, 2. So let's just, sorry, x over here. Let's just take the partial derivative of this with respect to x. So we get a 2xy. That gives me a 0. That gives me a plus 3 and another 0. Partial derivative with respect to y gives me a x squared minus 4y. Everything else gives me 0. Those are all treated as constants. And partial derivative with respect to z, well, these are all zeros and you have a minus 1, which is actually the same answer you'd get from another technique. And I'm evaluating that at the point 1, 1, 2. I should give us a name. It's what's called n. Yeah? Right. So let's just plug it in. We get n is equal to, I'll put in 1, 1. I get 2 plus 3 is 5. Again, put in 1, 1. I get 1 minus 4 is minus 3. And minus 1 is always minus 1. So that's my normal vector at the point 1, 1, 2. Alright, so if we have a normal vector and we have a point, then we can just use point normal form to write down the equation for the plane. I guess I'll work over here. So the equation for the tangent plane. So use point normal form, it will be, let's do it in 2 steps. So it's the dot product of the normal vector, 5 minus 3 minus 1, with the difference between an x, y, z coordinate and my point. That's x minus 1, y minus 1, z minus 2 equals 0. Now technically that is the equation, but I can expand that out to get a nicer looking thing. I think I just have enough space to get 5 times x minus 1 minus 3 times y minus 1 minus z minus 2 equals 0. And personally I think that is good enough, but maybe I'll see what Daniel thinks about that final answer.
I think this answer is, this is the equation for the tangent, well, one of many equations for the tangent plane. I think that's perfect. There's no real value in going from point normal form to Cartesian form, I think. Cartesian form is what they give you in the notes, but I think that is perhaps even a superior form of the tangent plane. Notice that this is, you've done this already in Math 1A. When you were given, perhaps some of you have done it in Math 1A, when you were given the equation of a plane, which is a linear function in x, y, and z. And then you computed the normal to that, which was just the coefficient of x, the coefficient of y, and the coefficient of z. So you have done this previously, but you only ever did it for planes. The nice thing about this method, I guess, is that it works for more general objects. The only thing you have to ensure is that you get your jumble of variables on one side of an equals, all together on one side of an equation, and call it f. And if you have constants, just throw them on the other side. And that way you can ensure that you can compute the normal quite easily. Cool, nice, nice.
So we get another 2-mark question, I think.
Was that 2 or 3?
3.
I think it was 3.
Let's see where oh, you're right. 3. Wait. Yeah, that seems to be 3 marks. Okay.
Yeah.
So there's room for 3 marks in here.
Okay, one has to be for computing the normal. I mean, there's several ways of going about this. One for the normal, I think one for the plane, and one for, I guess, doing this bit correctly. No, I guess knowing what to do in that sense. So if someone kind of knows that they need to do that, but perhaps messes this step up and messes this step up, then they can still get 1 mark, because just knowing how, in some sense, to compute the normal would be pretty good. Or if you're doing it the other way, just knowing what the formula is, I'd say it'd be worth 1 mark. And then wielding that formula correctly to compute derivatives, and then throwing it all into the equation to get the plane. Yeah, but just for a 3-mark question, I think 1 mark for just knowing what to do is appropriate, and then the execution for the rest of the marks.
Yeah. So So yeah, personally my preference is for this particular technique to make it a one function of fyz is a constant and get the normal this way. I think it's clean. It's really, I love the way this looks symmetric in all the variables.
I like it too. Okay, so this is probably the hardest question in any of the tests. It's a 4-mark question, so that will first of all alert you to the fact that this is probably going to be more involved than the previous questions. You're given some crazy function. Z is a function of the x's and y's, and you're told a measured value of x is 9 centimeters, another value y is 1 centimeter, and the error in this measurement is at most that. So maybe I'll just write that down. So I'll say, given that the error, so we know x is not approximately 9, but we only know that up to this error. So the difference between x and the value 9 is at most, this is what we're given. We don't know x exactly, but it's this close to 9. Could be 9 minus 3/100ths or 9 plus 3/100ths or somewhere in between. We also know that y minus 1 is less than 3/100. So this is all we know about x and y. They're more or less 9 and 1. Use the total differential approximation to estimate the maximum error in that. Well, first of all, to estimate z, and then the maximum error in that value of z. So if I give you values of x and y to be 9 and 1, first of all, what is z? So if x equals 9 and y equals 1, then let's call this x0 and y0. So if this is kind of our measured value, is 9 and 1, then z0 is, let's see, the square root of 9 . Good. So this is what we're given. Z is, if these measurements are exactly right, then z is 2. But the problem is there's some variation in this. So what could z be? First of all, let me do something a bit different that we've never tried before. So bear with me for a moment while I try something crazy. I'll just grab the microphone. Okay, so let's not that, go away. This one. Okay, so this is the surface. This blue thing is the surface z is equal to root x plus 1 over y plus 1. Here at the point A, I've got, this is the point 912. So this is the kind of point that we're talking about. The objective is to figure out where, what the possible error in our z measurement should be. Now, plugging these values into the equation we have for z is just crazy. We can't handle an equation like that. It's too complicated. So what we're instead going to do is plug it into the tangent plane. Because the tangent plane is something that has these terms in it, this x minus 9 and this y minus 1. It's got those terms in it. So we can actually use our estimates on the tangent plane to get an estimate for the error of z. And I'll just show you what I mean here. So here's the point A on the surface. If I get the plane, then the plane looks like that. And now if I zoom in closer, and closer and closer and closer. So something like this, and we can see that this blue surface here is looking more and more like the tangent plane. So instead of estimating my error using the surface, I'm going to estimate it on the simpler object, which is the tangent plane, and get a kind of approximation on the error. So that's what I'm going to do. Now let's go back to the stream. So I'll go with that. Top. All right. Okay, I'm back. So here's the value z. I'm just going to use the total differential approximation to do this. So that tells me that z minus z0, which is 2, is approximately equal to, now let's see, z dx, evaluated at 9,1 times x minus 9 plus this should be partial derivatives. Partial. Evaluated at 9,1 times y minus 1. So you can see here, I've got my x minus 9 term, and I've got an x minus 9 term here, I've got an x y minus 1, I've got a y minus 1 here, and this is the difference between my possible value of z and my estimated value of z. So I've got all the ingredients here in my total differential approximation. I just need to know what this stuff are and somehow work in the absolute values. So let's figure out what dz, dx, and dz, dy are. Of root x plus 1, which I can write, well, the y plus 1 can just come out the front, and that's the derivative of root x, which gives me half root x. So at 9,1 that gives me, so that's 2, and that's 2, and that's 3, so 1 on 12. dz dy of, I need to figure out what this is first, is d dy of, and this time I can just bring out the x plus 1, sorry, the root x plus 1. And the derivative of this is, now let's see, multiplied by the derivative, negative 1, y plus 1 squared. And now I evaluate this at the point. So dz dy, can you see that? Is 9,1. Evaluated 9,1 is 4 times minus 1 divided by 2 squared is minus 1. Right, so now I can at least simplify this equation up here. That's 1/12, that's minus 1. Maybe I'll continue down here. So z minus 2 is approximately equal to 1/12 times x minus 9 minus 1 times y minus 1. Okay. That's nice. This is essentially the equation of the tangent plane. You could have got this in another way, perhaps using the method you saw from Josh in the previous question. What I need to do is somehow work in these. I don't have the difference between x and 9. I have the absolute value of x and 9 and a bound on that. So I need to get my absolute values in here somewhere, and the way I'll do that is just use the triangle inequality. Notice what's happened to this minus, it's become a plus. And now I'm in a position to use this information which I was given in the question. So that's, well, I'll just write it out as 1/12 times 300 plus, which is equal to 3 on 100 times, which is, what is that, 39 over 12 times 100, which is, what's that? Which is 13 on 400. Oh, Josh.
Right. So actually there is an error in this.
Oh no.
It's not a big error. It's just the relation between these two statements is not correct. This should actually be a less than or equal to.
Ah. Yes, because these are actually less than. I accept. Damn, I lost half a mark. Did I lose half a mark? Maybe.
Well, it's hard to say. I mean, you had the inequality. Well, you did use the triangle inequality, which is a very important part. But it's kind of subtle that you are saying that this term here is bounded above by this term. So you're putting in the biggest value it could possibly be. So that's giving you a nice bound on this entire thing.
I guess the issue is we don't know where the real value of x is. It could be, this one could be real, it could be like,
Could be really 9.
yeah, it could be really 9, we don't know. But this one could be positive, this one could be negative, so you don't know. You don't know. There will be other questions where you do actually know the value of this, and maybe this one is positive, and maybe this one is in fact negative. And in those cases you can get a better bound, a more accurate bound. But if you only know the error in absolute value, then you need to use the triangle inequality, and your bound will be, well, I guess a bit looser.
Right. But yeah, I mean, it's a meaty question, and there is a lot you'll need to write down to answer this question.
Yeah, but 4 marks. How would you allocate those marks?
Well, I mean, I do think there's something they didn't tell you explicitly. I mean, the question does say it in words, but translating those words into these statements here, these mathematical statements here, I think there's possibly a mark in that. Well, so tangent plane, that's good. Definitely knowing that you need to use a triangle inequality. So
We think that one's good. Maybe I'll just put a 1.
Yeah.
1.
So possibly
Maybe
one
up here just for reading the question into symbols. I think this formula is probably worth something. There's a lot of stuff in this formula.
Yeah.
So maybe 1 there, and maybe 1 mark for just doing the derivatives.
Okay.
I mean, once you've gotten to this equation, I think it's just some arithmetic to get there.
Yeah.
So I would have. There's more work to be done here. I think actually taking that derivative might be tricky. So I'm thinking maybe something like that.
Yes.
Yeah. Do I get a bonus mark for my cool diagram?
No. Yes. Well, I don't know if I can work that into a test.
Maybe. Do not try and graph the thing they give you in the exam. No. Just apply it. It's impossible to kind of visualize this. Even GeoGebra has trouble. But you can. The whole idea is to simplify the curve you get by instead using its tangent plane, because the curve and the tangent plane are kind of close when the diff for x values that are small. Well, x values that are close to the point at which the function hits its tangent. Ha! You are?
Yep. So the next one. Look fine. Okay. Alright, so this last question is just a nice recurrence relation question. And they actually give you a recurrence relation here between this integral and another integral, but actually the first thing I want to do with this question is actually set up some notation. So, so I probably would just start by giving myself some nice notation to use. Let I(n) equal the integral from 0 to 1 of 1 minus x squared n dx. And I'm just going to translate what they told me into this notation. And we're given. So I think actually, personally I think it is helpful to write this down, just so you see exactly what the recurrence relation is. So it's going to be this in is equal to 2n plus 1 I, and this is actually just in minus 1. And let's just remember, this is only valid when n is greater than or equal to 1. So what is the question actually saying? Well, the question is actually just saying, in this notation, find I4. So, well, let's start as low as we can and build up towards that. So, if I want to, well, let's just start with what we actually can do. So, I1. So, according to this, I1 is equal to, we'll put in 1 here, you get 2 over 3 times I0, or 2/3 the integral from 0 to 1. Let's put in n equals 1 here, that's 0. This thing to the power of 0 is just 1, so it's actually just equal to this integral dx. So this is easy to do, it's 2/3. Okay, I'll do it as an actual proper integral. So it's the integral of x from x equals 0 to 1. So 1 minus 0 is 1, it's 2/3. Once you get used to integrals, you'll recognize that it's just, well, maybe you should already be familiar with that. Length times the constant here. Okay, well, I'm a step closer to finding I4. So let's now try and find I2. So what do I know? We were told that I2 is 2 times 2, so 4 over 4 plus 1, 5, times I1. It's 4/5 of 2/3. 4/5 of 2/3 is 8/15. That's not too hard to do. Alright, what about I3? Well, I3, according to this formula, is 6 over 7 times I2. Well, I know I2, it's 8/15. So it's 6 over 7 times 8 over 15. Now I can spot common factors in the 6 and the 15. So maybe I'll just, one step or two. Let's just do in a middle step, 2/7 of 8/5. Right, so that's 16/35. And one more step and I have my answer. And since this is an important answer, I'm just going to go with thus. I4, which is what we're asked to find, is equal to 8 over 9 times I3, or 8 over 9 times 16 over 35. I don't see any cancellation, so if I double 16 3 times, so multiply by 8, I get 2, 64, 128, I think. Yeah, 128. And this, 9 times 35, that's almost 10 times 35. I'm just 35 short of 350. I get 315. And that's my answer. So I think if I I think I'm happy if a student stops there. You define the notation, you got your answer. So I think that's sufficient. All right. Any comments?
I like it. That's my comment. I like using the recurrence relation in this way, so that you can. I've seen examples of people who like to do it this way. So they're given I4, and then they just start using the recurrence relation. And they write that as, say, 8/9 times I3, but they don't know what I3 is, so you have to write that as 8/9 times, and then use the recurrence relation again. That becomes 6/7 I2, which becomes, and you just keep using the recurrence relation all the way down. So 8/9 times 6/7 times 4 on 4/5 I1, and it just keeps going. I much prefer this, where you're actually starting from the base case and you're gradually building your way up to I4. So I like this. It doesn't leave you hanging, because at this stage I still don't know what any of these things are. It's only once I get down to I0 that I can actually perform any of these integrals and discover what I4 is.
One thing that occurs to me is I don't need to start with that. I didn't need to calculate I1 this way. Actually, I1 is also a fairly easy integral.
Yeah, you could have just straight up done I1. I like starting with I0.
Yeah, I think it's easier.
I prefer to do as little integration as possible. So yeah, I0. Yeah, and I think just leaving it as a product. Okay. I mean, it's a 2-mark question, isn't it?
Yeah, I guess I can't. An unsimplified product, sort of.
Yeah, I'd leave it as a product. So 1 mark for being able to wield the recurrence relation 1 time. So if you manage to get from here to here, I'd say great, they know what a recurrence relation is, they know what to do. And then another mark for just being able to do that a few more times. One thing I do want to say about recurrence relations is that, well, first of all, you're given the recurrence relation, so you don't need to prove it. Do not attempt to prove the recurrence relation. If you're told, given the recurrence relation, do something, don't prove the recurrence relation.
Actually, if you do look at the tests that this came from, it actually explicitly says at the bottom, do not prove.
Yes, so please don't prove it. The other thing I want to say is that the recurrence relation kind of encodes what would happen if you were to use integration by parts in this neat little package. So if you were just not told anything and asked to integrate this, you'd probably have to do integration by parts 4 times. But if you're given this recurrence relation, then you can kind of perform the operation of taking integration by parts in this really efficient way, and thereby get to I4. So integration, this recurrence relation is really just summarizing what integration by parts would do to your integral, and then allowing you to do essentially integration by parts 4 times really quickly. So I think recurrence relations are awesome.
Okay.
I think that's it for the test.
Yep, that's all the questions we've
Yeah, and it's been an hour, so there you go. Cool. So thank you all for watching. Good luck with your final exam, or your class tests.
Well, good luck with your final exam as well.
And
let's concentrate on the class test first.
Cool. Okay. Thanks for watching.
Cool.